Today we study motion in three dimensions. Until now, we have developed a way how to describe the position, velocity, acceleration in terms of the Cartesian coordinates. The Cartesian coordinates has a strong point. It has a merit that all of the axes are perpendicular to each other. The linearly independent three basis vectors called E1 hat, E2 hat, and E3 hat. They are all orthogonal to each other, and the orientation of the three vectors are chosen to satisfy the cyclic form, cyclic triad. So we, in the previous class, we have studied a lot regarding the orthogonality of the basis vectors in the Cartesian coordinate system. And in addition, this is for the scalar product. And for the cross product, we have studied the triple scalar product as a result. E1 hat cross E2 hat dot E3 hat equals 1. From this relation, we generalize this one to evaluate the determinant, and actually the cross product of two vectors were expressed in terms of uh, determinant. The reason why we studied further with the matrix algebra is the consequence of this relation that if we use the Cartesian coordinates, vector calculation reduces into the matrix calculation. And this is the fundamental relation for the basis vector for the Cartesian coordinate system. Today, we focus on the three-dimensional motion, but especially for the two-dimensional motion using polar coordinate system. Polar coordinate system is very similar to Cartesian coordinate system in the sense that the three vectors are orthogonal, but especially the two-dimensional case, we only need two linearly independent basis vectors that are called ER and E theta. This is for the radial, and this is for the tangential direction. Unlike the basis vectors for the Cartesian coordinate system that satisfies E I hat dot equals 0. That means direction of the basis vector and magnitude are all fixed relative to time. However, if we make use of polar coordinates, the direction of the basis vector depends on the angle. So its time derivative also depends on the angle and time. However, it is a very convenient set of basis vectors to describe the motion on a circle or in a general motion along a curve that has a curvature. But Cartesian coordinate system is quite convenient to employ the matrix representation. So we need to decide, depending on the situation, whether we use the polar coordinates or Cartesian coordinates. But we can all, as long as we want to translate, it is always possible to translate the information coming from the Cartesian coordinates to those for the polar coordinates. Displacement. Displacement is the change in the position. Change in the position I have x vector. If we employ Cartesian coordinate system, we have three linearly independent vectors called the Cartesian basis vectors and their corresponding coordinates. X coordinate, Y coordinate, and Z coordinate. If you want to describe the change in the position, that is the displacement, we put the subscript, the second position, and first position, initial position. The displacement is the difference, delta x. Here I wrote r, but they are equivalent. The difference, this is the x1, and this one is x2, and the difference is x2 minus x1. Then, because the Cartesian basis vectors are constant vectors, they vector out. And we end up with the difference of each coordinate. Many times we use just coordinate only. If you want to take the derivative with respect to time to find the instantaneous velocity, then we have to make use of Leibniz rule. A vector has a components. Time derivative for each term, and this is a product. If you have f times g derivative, f prime g plus f g prime. This is a Leibniz rule for the product functions derivative. However, E1 derivative, E2 derivative, E3 derivative with respect to time are all equal to zero vector, because Cartesian coordinate has a basis vector that is invariant. So the derivative is quite simple. The derivative of coordinate only. Okay. Velocity. Just like what we have done, we can find the difference of the position to find the displacement. If the time difference is finite, the ratio will give the average velocity. If the time difference approaches zero, we will obtain the instantaneous velocity, the derivative. If we make use of the Cartesian coordinates, because E1 hat dot, E2 hat dot, and E3 hat dot, everything is vanishing. What we have to do is take the derivative of components only, effectively. This one can be generalized to compute acceleration. The change in the velocity divided by finite time interval, you obtain the average acceleration. If you take the limit as delta t goes to zero, then you will find the instantaneous acceleration. Instantaneous acceleration. Again, E1 dot, E2 dot, E3 dot, they are all vanishing. The acceleration is just a double time derivative of components, keeping the basis vector the same. Let us consider the projectile function. You will find that the trajectory of a projectile satisfies a parabolic curve. There's a problem. You learned the parabolic equation in middle school, and it's not based on mathematics, it is based on physics. Nature gives the parabolic curve. The equation of motion is for the projectile is very simple. That's it. And we would like to introduce G on axis, E2 hat going up, and we can always choose the plane on which E1 is placed in this way. We have the initial velocity v0, or either we can write it x vector that. We can integrate this equation once from 0 to t. Then we have velocity at t subtracted by velocity at 0 equals g integral 0 to t. That is gt. Hence, x dot t equals x0 plus gt vector. If we integrate one more time, minus x0 dot is missing, x dot 0 dt 0 to t plus g constant 0 to t dt. Therefore, displacement at t equals 0 plus dot 0 t plus 1/2 gt vector squared. This is the answer. So to simplify our analysis, x, we restrict ourselves to E1 plus y E2, and we can get rid of the third component. It's a purely two-dimensional motion, if we can reduce always. All right. Then we can divide this one into x of t equals x E1 hat plus y E2 hat. And what is the x E1? X0 plus a V0 x component. V0 x E1 hat and V0 y E2 hat. Okay? This V0 can be decomposed into horizontal and vertical components. T. And third one, second component, E hat, Y0, V0 YT. And we have chosen the gravitational acceleration to be opposite to E2, so minus 1/2 gt squared. We find that x minus x0 equals v0 xt. That means that we can always eliminate time. X minus x0, v0x. And v0x, if we choose this angle to be theta 0, this is v0 cosine theta 0, x minus x0. And what about y? Y minus y0 equals v0 yt minus 1/2 gt squared. And we can make use of this time. We can substitute this one into here. Before that, we can rewrite this one v0 yt minus 1 minus 2 v0 y gt. So if we use this v0 yt equals v0 y x minus x0 v0 cosine theta. So that is, this one is a v0 sine theta 0. So v0 cancels. Tangent theta 0. So this one corresponds to this because x0, y0 are set to be 0. And what about this? At t equals 0, if we choose x0, y0 equals 0, then it flies in this way. Initial and final. We would like to know the horizontal range R. Then horizontal range R is a point when this one becomes 0. Because this is initially 0, y0 was 0 at that time. So again, it returns to the same point. So t gt over 2v0y equals 0. You know, t equals 0, so x minus x0 v0 cosine theta 2 times v0 y sine theta. Equals 1. We have g. Alright? So x minus x0 equals 2v0 squared cosine theta 0 sine theta 0 over g. And 2 cosine sine, that is v0 sine 2 theta 0 over g. So that is the range. v0 sine 2 theta 0 over g is the range of this projectile motion. Next, we consider a tangent to a circle. In two-dimensional motion, we frequently consider the circular motion, especially the uniform circular motion, until we study damping effect. The uniform circular motion says projection onto x or either y or x or y axis will give the simple harmonic motion. So this is one of the fundamental motion in physics. First, before considering the time concept, we just focus on the geometric concept for coming from a circle. If I have a circle, there's a center radius. So here radius is A. If I want to represent a point on a circle, I write the vector. This vector x must be expressed as radius A and unit vector ER, something like that. Because E1 hat, E2 hat are fixed, but if you change the position, the radial direction changes. That's the difference between this polar coordinate. This is a polar coordinate, a radial unit vector. Anyway, our basic constraint is that this length squared is constant. If the length squared is constant, why don't we find the differential of this? The differential is x squared is x dot x. This is a product. Differential is, for example, if you take the derivative with respect to x, then this one is called the differential for the function value, and this is called the differential for the parametric value. Then, if I take or want to take the derivative with respect to time, for example, what I would do is then I apply Leibniz rule. Leibniz rule gives this is what x dot x plus x dot. So that is 2 times x dot x dot. But this one can be written in the form. So if we multiply dt to find out the differential of this x squared, we find that differential of x squared is just 2 times x dot dx. The differential shows a simpler way because the parameter t does not have to be introduced. So regardless of any parameter, the differential is exact. Interestingly, the x squared is a squared that is constant. The right side differential of the right side is exactly 0 for in any case. Because it's exactly 0, what we find and on a circle, if there is a differential change in the position, is at the original position, x dot dx must vanish always. Although this is an infinitesimally small one, by definition is x magnitude, dx magnitude. Infinitesimal does not mean it is exactly 0. It approaches 0, but it is not exactly 0. It will never reach 0. Cosine theta equals 0. Because they are non-zero, this results in cosine theta equals 0. That means the radial vector, unit radial vector, and tangent. This is tangent. As if you make a differential of the position on a circle, then the track is along the tangent. So the unit vector along the tangent will be the tangential vector and radial vector. This radial vector and tangential vector must be perpendicular to each other. It is absolutely correct in any case. For a circle, this is quite important. So we only consider the geometry. So let us consider further by considering the time dependence. Position of a vector on a circle is a function of angle. There is a position x, this angle. Then this vector has a radius r and polar angle theta. This one has x component r cosine theta. This y component r sine theta. And we compute the velocity. The velocity, if we make use of the Cartesian basis vector, E1 hat dot and E2 hat dot are all vanishing. So what I have to do is take the derivative with respect to theta first and apply the chain rule, because it's completely determined by theta. So my time derivative can be computed. First, carry out the angular derivative and multiply the time derivative of angle. So it is written theta dot. So angle derivative multiplied by theta dot is the time derivative in this situation. So this is the chain rule. It's very useful for the computation of a motion on a circle. What about the second order derivative? If I do the second order derivative, I take the derivative one more time. If I take the derivative of the first one, I have the double time derivative of angle and single derivative of theta. And then I can take the time derivative, the whole object one more time. Then I have theta dot. And then we have theta dot. This one. Theta dot, in case theta dot is independent of angle, then you can pull this out. That is consistent for the uniform circular motion. And then Leibniz product rule can be used. So we have repeated the derivation so many times. The Leibniz rule can be applied for the scalar product, because the scalar product can be decomposed into the components using Cartesian coordinates. Then this is each term is a product, and product function as derivative, first one and second one. And if we recombine everything all together, this one becomes a dot b, dot b, and a dot b dot. This is true for the linear combination of two vectors with the time-dependent coefficients, scalar coefficients. So similar application can be made to find these formulas. Let us consider uniform circular motion. Uniform circular motion is a motion of a particle on a circle of radius r, fixed radius, and angular frequency, the angular velocity of the particle is also fixed. That means the angle measured from the x-axis counterclockwise is omega t, so proportional to time. So in that case, the calculation becomes quite simple. First, we write down the position of particle with a fixed radius and multiply it by the unit vector, that is the unit vector along the radius. So this one is the unit radial vector. And angle theta, as we have stated, theta is omega t. The rate of changing depending on time is fixed as omega. That is angular frequency or angular velocity. This one we call the uniform circular motion. Uniform means the angular frequency is constant. Constant angular velocity. If you want to compute the velocity or acceleration of a particle under uniform circular motion, then you had better take the derivative, time derivative in terms of angular derivative and multiply d theta over dt. So this is a way to compute the time derivative in uniform circular motion. As you know, cosine and sine that can whose the time derivative is actually theta is a function of the time. We can take the derivative with respect to theta, that is a minus sine theta, cosine's derivative minus sine theta, and then multiply theta dot. Theta dot is omega fixed as a constant in the uniform circular motion. In a similar manner, sine theta's time derivative can be obtained by cosine theta and multiplied by theta dot, that is omega. Basis vectors of 2D polar coordinates. This, in comparison with Cartesian coordinates, whose basis vectors are constant of time, this radial vector ER and unit tangent vector, tangential vector, E theta, they are always making a right angle. So they satisfy the orthogonality. And magnitude of ER is 1. Magnitude of E theta is also 1. And they are perpendicular to each other. This is the same as the unit basis vector for the Cartesian coordinates. All right. So, because ER, unit radial vector, makes the angle theta with the x-axis, this E1 component, this direction is E1, and this direction is E2. And its component is cosine. And the y-axis is over here, and it makes 1/2 of pi minus theta. So it's saying this direction cosine is cosine. This is sine theta. So that's the reason why we have sine theta as a coefficient. In a similar manner, we can write down the Cartesian components of unit tangential vector E theta that is making an angle theta with E2 and making 1/2 pi minus theta with minus E1. So we have minus sine theta for the component of the x-axis component, and for the y component we have cosine. So in summary, we can either write down E1 hat in terms of I hat and E2 hat as J hat. So this one and this one, they are equivalent. There is another way to derive the unit basis vector, that is by taking the partial derivative. Radius is x vector, that is r times er, and this er is a function of theta only. So if we change the r only, it is partial derivative, and this is independent of r. So as a result, this is 1. So unit radial vector can be obtained by taking the partial derivative of radius. So this is the unit radial vector. What about the e theta? We have er here, and if we rotate by angle, very small angle, it becomes er theta plus d theta. And this is a circle. And if this angle is very small, and because this radius is a unity, the arc length is d theta. Therefore, the vector, this vector is proportional to e theta hat as the d theta goes to 0 because it becomes tangent, and length is d theta. All right? So what's that? E theta hat d theta equals er's partial derivative with respect to d theta. So we can cancel this, find out that e theta hat equals unit radial vectors partial derivative with respect to angle. As we have already stated, er and e theta, they are perpendicular to each other, and each length is 1. Next, we consider the time derivative. If we make use of this, e theta hat equals er's theta derivative. In a similar manner, er hat e theta's theta derivative. However, this is r and this er and e theta. If we change the er, the change is parallel to e theta. However, if we change e theta, its direction is opposite to er. Therefore, we need to put the negative sign on it. That's quite important. As a result, er dot goes by chain rule, this one, and this one is theta and e theta. So er dot equals theta dot e theta hat. What about e theta dot? That is theta dot partial derivative of e theta. And this one is a minus er minus theta dot er hat. So e theta dot equals minus theta dot er hat. If you repeat one more time derivative, er double time derivative is e theta double time derivative e theta, and this is e theta and its time derivative, that is theta dot minus er. So the answer is theta dot e theta, theta double dot e theta minus the theta dot squared er. In a similar manner, we can also compute this, but right now, in here, this one vanishes because the theta is omega t, then theta dot equals omega, and theta double dot equals 0. So these are the results. You can repeat the same calculation with this differentiation table. Velocity and acceleration. So we have already found the double time derivative of unit radial vector is like that. And in a similar manner, the double derivative of the angle, the polar angle vector, is written in the form. So let us first compute the velocity. Velocity is the displacement. First write the position and time derivative, x dot. Then Leibniz rule. And this one is r dot er head, and this is r theta dot e theta head. If I take the time derivative one more time, r double dot er head. If I take the time derivative, this is theta dot r dot e theta. Here I have r dot theta dot e theta and r dot theta double dot e theta and derivative of e theta hat is minus r theta dot squared er hat. If we consider similar term d theta 2 r double dot minus r theta dot squared, and tangential components, we have these two terms, 2 times r dot theta dot and r theta double dot. This is angular acceleration. This one is a radial acceleration. If a particle is not going straight, but following a curved path, then there should be some force toward the center of the circle. That is called the centripetal force. This is acceleration. This one we call toward the center, omega squared. This is a centripetal acceleration. Another term in here, this is called the Coriolis acceleration. Radial component of acceleration is here. Tangential component of acceleration is here. If you have a uniform circular motion, theta equals omega t, theta dot is omega, and theta double dot equals 0. Theta double dot equals 0. In that case, we have theta dot equals omega. Okay. As far as the velocity is concerned, where is the velocity? Here. So radius is fixed, so r dot vanishes, r theta dot, and the theta dot is omega, so r omega. This is our acceleration. Theta dot equals omega, r dot equals 0, r dot equals 0, r dot equals 0, so only this one, minus r omega squared toward the center is the acceleration that is called the centripetal acceleration. Period, it is a repeating. So this function is a function of sine or either sinusoidal function, sine or cosine, that has a periodicity, that is omega, is fixed. Give some time to pi. Sine, 0, and pi, they are the same. So this one is repeated. So omega t becomes 2 pi. That means the time scale, 2 pi over omega, is the period. And omega, in that sense, the periodicity, since we say omega is angular frequency. But it is also coded as angular velocity. For the uniform circular motion, we have a special relation. Next, we consider Galilean relativity. Let us study Galilean relativity. Galilean relativity is the basic postulate of Newtonian mechanics. Galilei is the first person who introduced the observer. That means a frame of reference to measure some physical quantity. So Cartesian coordinate system, the coordinate system, whether it is Cartesian or polar coordinate system was first introduced by Galilei. Suppose that you measure the position of the two frames. There are two persons. One person is a frame of S at the origin of the frame of S, and the other person is at the origin of a frame of S prime. So we use, here it is written as SA and S, whatever. So this person's position is at the origin of this axis, coordinate axis, and to an observer in the frame S, the displacement, the position vector is RA. And these two persons in the frame of S and this in the frame of SA, they observe another, the third object. The displacement or the position vector of this object is RP, and when it is seen at S, and the position of this object when it is measured in the frame of SA, and it is called to RP/A. The slash A means who is the observer. Here we find a triangle. We find it RA plus RPA equals RP. So RPA equals RP subtracted by RA. This means whatever observer may be, once it is measured, there's a position, but if you replace the observer, then what you have to do is subtract the position of the new observer in terms of the original observer. So slash A is indeed is RA subtraction. In this manner, object's position, velocity, acceleration measured by A can be expressed in terms of position measured by another person in the frame of S, subtracted by the position of the second observer, seen from this original reference frame. Let's say it's RA. This should be subtracted. If you take the time derivative, what you have is the velocity of the particle, and right side, they become this position is replaced with velocity. That is the time derivative of this particle, Rp, measured in S, and this Rpa measured in the frame of SA. And time derivative, it becomes, they are replaced with this one is a VA, this one is a VPA, this one becomes a VP. In a similar manner, we can make another time derivative, then velocity will be replaced with acceleration. So here, if VA and VB are constant, VA means velocity of A and the particle's motion. Another, we have observer A and we have another observer B, then this subtraction, acceleration, in the case of velocity, there is some change, but in the acceleration, if the velocity of an observer, the reference frame, is a constant, second order derivative of that observer becomes vanished. Therefore, acceleration measured in this frame and this frame, every frame will be the same. This is called the Galilean invariance. That means law of inertia is true in any inertial reference frame. That means inertial reference frame means in the frame whose origin is not accelerating. The origin of a frame that is not accelerating. That means that is at rest, either at rest or moving with a constant velocity. So we can describe any physics phenomena in any inertial reference frame with the same acceleration, although there is a relative velocity, non-vanishing relative velocity. The Galilean transformation assumes two important constants. There are two. One is time is invariant. The other, mass of particle is invariant. Unfortunately, both of them are wrong in the sense of Einstein's relativity. If the velocity of particle is very fast, it is quite comparable to the speed of light, then this the time dilation emerges. So the two frame of reference have different scale of time flow. In addition, due to that time dilation, it results in the change in mass of a particle. So the Galilean relativity is absolutely wrong in the completely general sense. However, if the speed of an object is relatively small, very small in comparison with the speed of light, the Galilean relativity is still correct. Not exactly correct, but there is no way to distinguish any error in it. So that's the reason why we still learn Newtonian mechanics first, but later, in the next semester, Y22 through 24, we will study Einstein's relativity and how the Galilean relativity breaks down and how it is replaced with the correct theory That is called Einstein's relativity. Non-inertial reference frame. If the frame of reference is not accelerating, the acceleration is always the same for any observer. So it is very important to note that we have to be in an inertial reference frame. Although we are not in an inertial reference frame, there is a way to how to translate the value from the that measure in an inertial reference frame to another. What we have obtained previously is the equivalence of invariance of acceleration is due to the neglection of acceleration of each origin of the reference frames. However, if the reference frame is accelerating, then the acceleration is not invariant. For example, a falling body, it feels it does not feel any acceleration at all, and it feels that the Earth is approaching the object with the opposite direction of the gravitational acceleration. However, for an observer who observes the free falling body, the person knows that free falling body is accelerating. So this is an example of a non-inertial reference frame. In a non-inertial reference frame, acceleration may change. The disappearance of gravity in the free falling body is closely related to the equivalence of the Newtonian mass for inertia and the Newtonian mass for gravity. Happen to be the two absolutely different mass cancel exactly. That's the main starting point of the general relativity of Einstein. Okay, at the end of this section, we study, we review what we have learned in the previous in this class, and let me review a little bit. We studied the motion of a particle in a circle. In case we have a uniform circular motion, r dot equals 0 and theta dot is constant. However, in general, these radial component and the tangential component may have the general form. I have already told you that this one is related to the centripetal force. However, in the frame where this radial acceleration, this one becomes 0, radial acceleration becomes 0, means it is r double dot is r theta dot squared. Because this frame of reference is not an inertial reference frame, it is a non-inertial frame, so we experience some fictitious force. Even though it is not a force, it looks like force in the coordinate artifact of the coordinate. That is called the centrifugal acceleration. In fact, this is a condition of vanishing radial acceleration. That vanishing radial acceleration is causing the non-inertial, the inertial force. I mean, the force, the fictitious force coming from the non-inertial reference frame. In a similar manner, we have this condition. This is tangential component of acceleration. If it vanishes, we find this is carries the negative sign. So this is closely related to the Coriolis acceleration. When the wind blows in the northern hemisphere, it is not going straight, but going further to the right side of the forward direction. The next one is related to the measurement of the speed of light by Michaelson. And Michaelson and Moldy have carried out a very accurate experiment for measuring the speed of light, assuming that there is a medium of electromagnetic wave. Unfortunately, they were not able to find out such kind of medium called ether. Because of this absolute failure, he became the only person who won the Nobel Prize for the failed experiment. But this failed experiment is a new breakthrough of a new era called relativity. The speed of light is believed to be and measured to be the same for everyone whoever measured the speed of light, it is always the speed of light. That's it for today. Thank you.